So after having done that, we're going to go and we're going to talk about what it means, how we can find the angle between two vectors. So remember, in our conversations before, we said, we kind of touched on the angle between the two vectors, and we saw that it sort of did matter, right? What was the one angle degree that we talked about with this dot product? And we said it made a difference. If the angle was what? You got a dot product of what? What did we talk about? Just in the page prior. Here. What did we talk about here? That if the angle between them is what? 90, then it's then the dot product is 0, right? Okay. Okay, so if the dot product is 0 when the angle is 90, right? That means the angle makes a big difference, right? So look at what happens here. If I've got this one vector A and this one vector B, all right, and if they're perpendicular, the dot product is now how much? 0, right? When they're perpendicular, the dot product is 0, right? Because how much of a shadow is this casting on the bottom here? 0. So now, if I were to decrease this angle, okay, what would happen? Suppose I decrease the angle, and so now this is vector B. Okay, if this is vector B, what happened to that projection? Is there more of a projection than 0 or what? Now there is more of a projection, right? So the dot product is no longer 0. It's now this vector times however much that is, right? If I made the angle even smaller, now the projection is this. So what's happening to the dot product? Getting bigger or smaller? Bigger, all right? And when the angle is even smaller, what's happening to the dot product? Bigger or smaller? Bigger. When does the dot product of those two vectors become a maximum? When the angle is 0, right? When the angle is 0. So here, when the angle is 0, look at that. Now that green one is vector B, right? And the angle between them is 0. So now the projection is this much. It's the entire darn vector, okay? Times vector A. We're here now, okay? So now, when the angle is 0, the dot product is maximum, right? When the angle between the two vectors is 0, the dot product is maximum, because here there was no shadow being cast when the angle was 90. But now when the vector is laying on top of the first vector, the angle between the two of them is 0, and now the shadow times this, it's the maximum it could be. And so when the angle is 0, the dot product is maximum. And we had said when theta equals 90 degrees, dot product is how much? 0. Okay, so, well, hang on just yet. Okay. We are going to talk about that though. So now here's the question for you. We're talking about theta. Theta like lends itself to sine, cosine, tangent, right? Which one of those fits this description? That when theta is 0, right? It's a maximum, and when theta is 90, it's 0. Which one of the sine, cosine, or tangent fits that description? So for which one? So for example, which one is it that, like, let's say the sine of 0 would be maximum, and the cosine and the sine of 90 would be 0? Cosine, do we agree? Is cosine of 0 maximum? Cosine of 0 is maximum. What's cosine of 90? 0. Right? So let's think about that. Okay? When the angle is here, 0, we want the function to be a maximum. And when the angle is here, we want the function to be 0. Does cosine fit that description? Is cosine of 0, 1, and cosine of 90, 0? Yeah, okay, so what does that tell you? So now we did work backwards, right? We did work backwards, and we thought to ourselves, wait a minute, if the dot product conceptually follows this pattern, right? Then if I have to come up with a formula for the dot product, it must be somehow related to a cosine and not a sine. Isn't that a beautiful thing that you could do that? Like seriously, right? Look at that. Like we went all around doing this, you know, seemingly pointless thing, and then all of a sudden, oh my goodness, yeah, so it must be a cosine, right? Okay, so then, what would happen if it was 180?
It'd be the minimum.
Would it be the minimum?
Yeah.
Like minimum how? If minimum is 0.
If maximum is 1, then the minimum is negative.
Okay, so right. So if this is vector A, and if we made vector B here, right, and that's 180 degrees, now, right, you've got the, what do you call it, length of this, you've got the length of B, right, but there is it's a negative value, okay? Alrighty, so let's now, okay, so we did this conceptually, and we sort of figured out that this must be connected to a cosine, all right? And like we said, that was a beautiful thing to do. This is how most of these things come into play, right? You say, okay, you know, this is what, now let's see if the math works out. So now let's see if the math worked out. Let's derive a formula for A dot B. So remember what A dot B is. A dot B, right, that's the dot product. This is the length of the projection times the magnitude of B, right? That's what A dot B is. Okay. All right. So A dot B, let's see what it is. So if you have this triangle here, right? Vector A, and this is the projection here. If I were to draw a line perpendicular here, now I've created a right triangle, and right triangles are my favorite things to do, right? So what is this projection that I'm talking about? The length of the projection is that it's that red line, right? How big is that red line? If this is A, right, how do I connect the red to this? It's the side adjacent to the angle, right? So is it sine or cosine? Cosine. So cosine of theta is this over this, which means I say that that red one is A cosine theta. Just like when we were doing the vector projections, remember, like the rectangular projections, it's A cosine theta. So now, if I want the length of the projection, then that's A cosine theta. Okay? And then I need the magnitude of B. Well, for that, I'm just going to put magnitude of B because I could just find that. Okay? So what is this A here? What is this A? It's how long vector A is, right? So can I write it this way? Yeah, I will. So now A dot B is equal to A times B cosine theta. All right, so that's what dot product is. Now, earlier we had another formula for A dot B, right? What was it? It was A1 B1 plus A2 B2. This is if vectors are in component form.
That's how they do it when they're not in component.
Yeah. Most of the time in real life, 99.9% of the time, they're not in component form. They're not, okay? 99.999% of the time, you just have the length of a vector and then the angle in between, and this is how you find A dot B. Okay? So when given vectors and angle. So not in component form. Okay, so now if this is A dot B, right? Then can I solve for the angle? Can I solve for the cosine of this? Right? If I divide by magnitude of A, magnitude of B, then I get A dot B over magnitude of A, magnitude of B, that's equal to cosine of theta. So this is to find angle between vectors, right? And just like we said, it is a cosine. We already figured out that it was cosine because we knew it would be 0 when they're perpendicular or orthogonal, and maximum when the angle is 0. Okay? All right. Once you know that, it really becomes, like, to find the angle, it really becomes a straightforward calculation. So here, it says to find the angle between vectors u and v to the nearest tenth of a degree. All right, well, cosine of theta, I know, is u dot v over magnitude of u, magnitude of v. So again, it's just plugging numbers in at this point. Yes? It is. So we sort of have a choice, right? To find the angle theta, there is only one thing you could do, and that's to find u dot v and so on, right? So right now we're given information. Yeah, it's asking for the angle, correct. Okay, so u dot v is going to be 1 times 2 minus 4 times 6, minus because it's technically plus times negative, all right? So u dot v is negative 22. Now I need magnitude of u, which is 1 plus 16, root 17. Leave it that way because it says to the nearest tenth of a degree, which means there's calculator involved. You don't want to, cause any like rounding error here. V, magnitude of v is 4 plus 36, root 40. Now, if this was not on a calculator section, you would have to simplify that root 40 and make it 2 root 10, right? But if it's on the calculator section, then this is good enough. So cosine of theta is negative 22 over root 17 times root 40. All right, and we need to find theta here. So can somebody plug in, yeah, the inverse cosine of this? So it's inverse cosine negative 22 over root 17 times 40. You could put it in one root, and we want it to the nearest tenth of a degree. So let's go ahead and plug that in. All right, so theta here is 147.5. Okay, now for the biggie. Does this make sense, right? Do I have to take like the reference angle? Does this make sense? Well, let's see if it does make sense. Here's one vector. Okay, vector u is at 1 and negative 4. Here. That's vector u, right? And what's vector v? It's at 2 and 6. Here. That's vector v. What am I looking for? What is it that I'm looking for? I'm looking for the angle between these two. Does that make sense that that's 147 degrees? Yeah. That's pretty cool, isn't it? Yeah. Okay. All right. So let's do some deriving. All right. So let's talk a little bit about projections. Okay. So now what we're gonna do is we've said that, okay, the dot product is the length of the projection times the length of this vector. So now you see that red line here, right? That's the projection. Okay? What if I wanted to find that in vector form? What if I wanted to express that in vector form? That means I need two things to make it a vector. What does a vector consist of? Magnitude and starts with a D. Direction. A magnitude and a direction. So I need to find the magnitude of this, right? What is the magnitude of this? It's in that diagram. What's the magnitude of it? How long is it? How much? A cosine theta. And now I need to find the direction of it. What does it have the direction of? What does it have the same direction of as?
Vector B.
Vector B. Okay? So this has a length of A cosine theta, and it's got the same direction as vector B. So somehow I need to give it the direction of vector B with its magnitude. Remember a little while ago we talked about having like a little vector in your pocket that the only purpose of it is to give something the right direction? What did we call that? It had no magnitude. It had a magnitude of 1, but a direction. What's a vector that has a magnitude of 1, but it's got a direction? Yes, that's the one. What is it? It's a unit vector. It's got a magnitude of 1 unit, but it's got a direction. So somehow what I need to do is I need to create a length the same as this red one, but then I have to tack onto it the unit vector of B in order to like fix a direction. All right? Because if this pen is the correct length that I'm looking for, how do I know how to point this? Well, I tack it onto that unit vector, and now it's like fixed forever. All right? So I have to do the length of this, A cosine theta, times the unit vector of B. Okay? And look, this is what all of this says. All right? Look at this formula here. All right? What is the projection? A cosine theta, right? So if I have A dot B, if I divide it by this, I have A cosine theta, right? So look at how we started. We said A dot B is equal to magnitude of A cosine theta times magnitude of B. Now, if I divide by magnitude of B, I have A cosine theta. Okay? So the length is A dot B over B. This is the length of the projection. The absolute value, huh? Here, I divided by the same thing. Okay? So now I need to multiply this now with the unit vector for B. What's the unit vector for B? It's this thing. This is the unit vector for B. So now I take the length of the projection times the unit vector, right? And look at what I have. If I multiply the bottom here, all right, I have unit magnitude times magnitude, magnitude squared. So this is the projection. All right, so let's do projection here. All right, so what do we need for the projection? We need U dot V, which is what? -4 plus, -4 plus 30, 26. And then I need magnitude of U. Do I need magnitude of U? I need magnitude of V, which is 16 plus 36, root 52. So now, I need the projection of U onto V. This is U dot V over magnitude of V squared times vector V. Okay? All right, so let's see what we're going to get here. U dot V is 26 over root 52 squared times the full-blown vector B. Because I need a vector. I really need a vector. So, how much is this one? 26 over 52. How much is that? 1/2. 4 comma 6. This is 2 comma 3. Okay? So that's the projection of U onto V. All right, you know what? I'm going to give this another name. If the other vectors are U and V, I'm going to call this W. How about that? Okay, just call it W. I'm giving it a random name. I could have called it, I don't know, X.
Oh, so that's just like the little seven.
That's the, it's a projection, yeah. So if this is U, and if this is V, it's that vector here. I'm going to show you guys right now, actually. Okay, now look at what this says. Write U as the sum of two orthogonal vectors, one of which is the projection of U onto V. So what I have to do is I have to write U as the sum of two vectors. So I have to write U as something plus something else. One of it has to be this projection. What letter did I give the projection? W. So it has to be W plus some other vector Z. Okay? So what is vector U? It's -1 comma 5. And I have to write it as vector W plus another vector Z. Yeah.
For the other vector, can you do the opposite? Like use that projection again?
No. As usual, yeah. Okay, so now how do we find Z? What am I supposed to do? Subtract. So what's Z gonna be? If I subtract -2 from both sides, it's -3 comma 2. So then U is 2 comma 3 plus -3 comma 2. Okay, let me show you what it is that we're doing here. All right, so here I want to put on here vector U. All right, what color should we make vector U? Let's make it, okay, we'll do purple and then we'll do green for the other one. Okay, so this is vector U and it's going to be -1 comma 5, right? So I start from the origin and I'm going to go -1 and up 5. 1, 2, 3, 4, 5. Does that make sense that that's vector U? Okay, green for the other vector now, V. Let's do this green. Okay, V, how much is V? 4 comma 6. 1, 2, 3, 4, 5. Oh, no, sorry. 1, 2, 3, 4. 1. Is that 6? Okay. So that's vector V. Okay. Now, projection. Right? What's the projection here? 2 comma 3. Is that right? We found that the projection was 2 comma 3. Okay, what is the projection conceptually? If I were to shine a light on this, right, it would like lie along this, all right, and it would have the length of that shadow. So let's see what 2 comma 3 look like. What color should we make that one? Okay, red it is. We're gonna do 2 comma 3. Look at this. So now this is the projection. 1, 2, comma 1, 2, 3. Look at that. Look at how perfectly it aligns, right? So that is the projection of U onto V. Okay? What did we call that one? We called it W. Oh, it's not perfectly aligned. No, it is 2, 3. Okay. So we called this W. All right. Then what did we do? Then we said U is equal to, right? Then we said U is equal to W plus Z. All right. Now let me draw that vector Z, right? In black. That's negative 3, 2, in blue. Negative 3, 2. Negative 3, 1, 2, 3, 2. Okay? And then what did we say? So if this is Z, we said U was equal to W plus Z. Okay? Where is W? It's this one here. And where is Z? It's this one here. Let's add these two vectors and see what we're going to get. How do we add vectors? You add vectors by taking one and putting it as a continuation of the other vector, right? So let me do that. Let me take this and put it as a continuation of the other vector. And look at that. Look at how it makes U perfectly well. And guess what? Guess what the angle is between these two? 90 degrees, because their dot product is 0. Okay? So if you were to cast a light onto U, okay, if the sun was shining this way, perpendicular to V, that red W would be the shadow, the projection of it. And that plus this vector makes U. Isn't that cool? Right? So look at how perfectly it all aligns. Okay, so now, what's the big deal? Why do we use this? Okay? Why do we need vector representations, and why do we need dot products? Okay, well, have you guys ever heard of force? You've heard of force, okay? In science, have you learned about work? When you do work, what is work? How does work happen? It's got this. Okay, force times distance, it's energy, it's force exerted on it's force exerted on a certain object that makes it move. Okay, so now we're hitting on important things here. So if I were to apply force on this wall, but it doesn't move, how much work have I done? None. If I were to exert a small fraction of the force I exerted on this, if I were to exert that small fraction on this mouse and it moved, have I done any work now? Now I have done work. So work is force applied on an object which makes the object move. Furthermore, in order for it to count as work, the force that I apply onto an object has to be in the same direction as the motion. Right? That's the little bit there. So if I were to, if I needed to move this desk, I would push on it, right? Now, I could push on it at an angle, or I could just like, sit like this and push horizontally, okay? Either way, the desk is gonna move horizontally, right? It's the same motion. Now, when I exert diagonally, right? That's a diagonal vector. I have some of my force going in the vertical direction and some of my force going in the horizontal direction. The part of the force that's in the vertical direction is not doing anything to contribute to the work I'm doing on this object. Okay? Only when it's in the same direction does all of it count as the force that's making the work. So what does that remind you of? That only the part in the same direction applies here, right? So if I were to push only horizontally and it moved horizontally, what's the angle between the two? 0, okay? And this means all of the force that I'm using is being applied into the work that I'm doing. What does that remind you of? that if the angle between the two are 0, then all of it is being used. I'm sort of getting like maximum value. That's dot product. That's what dot product is. So, work is force times distance, you said? It is force times distance, but you know what? Work is not force times distance. Work is actually force dot distance. In real life, in real physics, work is not F times D, work is F dot D. All right? So, if you have an object here and you apply a certain force on it, you've got some of the force that's going down, that's being wasted. That's not doing anything to move the force and to move the box in the horizontal direction. Only the part that's going horizontal, only that X component is contributing to the work that you're doing on this. Yeah, but it still doesn't take it still doesn't take away from the fact that that component of the force is being applied to the work. You're still doing the same amount of work, no matter how much friction there is. That just affects the motion. All right? So, here, a person pushes a box with a constant force of 40 newtons at a constant angle of 45 degrees. All right? So find the work, this should say find the work done in joules to move the box 12 meters. Okay? So what did we say? Okay, so when you're in 6th, 7th, 8th grade and you talk about work, it's force times distance. But then when you get to real life, real physics, then work is force dot distance. So now, force is a vector quantity. We know that. Distance is obviously a vector quantity as well, right? Technically, it's not force times distance. It's force dot displacement. Okay? F dot D, the D is displacement, not distance, because that's the vector quantity. So force dot displacement, F dot D. And so if force is a vector quantity, displacement is a vector quantity, when we take their dot product, that's work. Work then, is the dot product vector or a scalar? Scalar. When you take the dot product of two vectors, you get a scalar. So in reality, in physics, in real life, work is a scalar. It has no meaning. Direction has no meaning for work. Okay? All right. So if work is F dot D, what's another way to write A dot B or F dot B? It's F D cosine theta. Okay? So F is 40 newtons. D is 12 meters. That's how much the box has moved. Times 45 degrees. Oh my goodness, that's blasphemous. Times cosine of 45 degrees. All right? This could totally be done without a calculator, by the way. Am I right or am I right? I am completely right because
Guys, 100% this is on the non-calculator section.
okay. So what is this? How much? Well, I'm going to put it in the calculator and I'm going to get 339.4 Newton meters. Okay. Why Newton meters? Because it was 40 newtons times meters, and then 1 Newton meter is a joule. So this is 339.4 joules. That's what a Newton meter is. Okay. A Newton is a derived unit, right? Kilogram times meter per second squared. And then this is kilogram times meter per second squared times meter, which is a joule. Okay. All right. So, whoa. So this is one method. Okay, let's do using vector components. You should know both.
Well, you asked us to use one piece of theory. do not.
Possibly. You should know both. All right. Using components. What's the... Okay, so we have a force vector and a displacement vector. So if this is moving horizontally, let's do the displacement first. What's the displacement vector if this is just moving that way? 12, comma 0. Good. Because it's moving in the horizontal direction, no vertical direction. All right. And if the angle here is 45, right? If I have a force vector and the angle of it is 45, then how much is the component vector, component form there? It's 40 cosine 45, 40 sine 45. So now, if work is F dot D, okay, then it's 40 cosine 45 times 12 plus, oh, one of these is negative. Which one of these is negative? This one. The y is negative. So minus 40 sine 45 times what? 0. Do you see how? Even in the math, everything in the negative direction just goes away because there is no motion in that direction. Do you see that? That's so beautiful. Why aren't you guys as excited about this as I am? Right? So anything, only the part that's in the same direction of the motion stays. All right? So then we still get 40 times 12, which is times cosine 45, which is 339.4 still in joules. Okay? All right. So this is homework.